So, when we talk about an AI being accurate, what do we actually mean? You might think it's just a simple score, like 95% right. But the real story? Well, it's more like a constant battle, a tug-of-war between two opposing forces. And honestly, getting a handle on this battle is pretty much the key to understanding how AI works at all.
I mean, we've all seen those crazy headlines, right? An AI can compose this incredible, beautiful piece of music, and then in the next breath, it looks at a picture of a chihuahua and says with total confidence, "That's a blueberry muffin." How? How can something be so brilliant and so, well, so dumb at the same time? That's exactly the question we're going to dig into today.
Okay, so before we can really get into the mistakes, we have to agree on what success even looks like. Let's use an analogy here. Think about archery. See, a perfect prediction from an AI isn't just about hitting the target somewhere. No, it's about hitting the dead center, the bullseye. It's all about being precisely right.
And this is where we have to draw a really, really important line in the sand between two ideas, accuracy and precision. Accuracy is pretty straightforward, right? It's just how close your shots get to the bullseye. But precision, that's different. That's about consistency. It's how close your shots are to each other. Just imagine this. You could be an incredibly precise archer with all your arrows landing so close they're touching. But if that tight little cluster is way off in the corner of the target, you're precise, but you're not accurate at all.
All right, so if hitting that bullseye is the goal, why is it so darn hard for AI? Well, it's because every single model is up against these two big enemies, these two forces that are constantly trying to pull it off target. And their names are bias and variance. First up, let's talk about bias. The best way to think about this is to imagine you're a sharpshooter, but the scope on your rifle is misaligned. It's a consistent, systematic error. It doesn't matter how perfect your aim is, how steady your hand is, every single shot is going to be off in the exact same direction. It means your model is working off a fundamentally flawed assumption about the world.
And the result of that misaligned scope? Well, it's this. You end up being precisely wrong. See that? A nice, tight, consistent group of shots, but the whole group is way off from the bullseye. The model is making the same exact mistake again and again and again. It's consistent, but it's consistently wrong.
Now, in the world of machine learning, this problem has a name. It's called underfitting. It basically means the model is just too simple to understand the complexity of the data you've given it. It's kind of like trying to trace a beautiful complex curve using nothing but a short, straight ruler. It's just not the right tool for the job. It can't capture the real pattern.
Okay, so that's bias. Now for enemy number 2, variance. And this is a whole different beast. This is all about inconsistency. So forget the misaligned scope. This time, imagine your scope is perfectly aligned, but you've got a really unsteady hand. Your aim might be centered on the bullseye on average, but each shot you take is unpredictable. It could land anywhere. And when we look at our target, this is what high variance looks like. You're sort of generally right, but you are completely imprecise. Your shots are just scattered all over the place, all around the bullseye. Yeah, the average of all those shots might be dead center, but any single prediction you make is totally unreliable. You just don't know where it's going to land.
This scattershot pattern is a classic sign of the opposite problem, overfitting. This happens when the model is too complex. It hasn't just learned the important patterns, the signal in the data. No, it's gone a step further and has basically memorized all the random meaningless noise as well. And because it's so perfectly tailored to the data it trained on, the moment it sees something new, it just falls apart. It can't generalize.
Okay, so we've got our two main enemies, bias and variance. But here's the million-dollar question. How do you know which one you're actually fighting? You need a better scorecard, right? A way to measure your misses that's a bit more intelligent than just hit or miss. You see, a simple accuracy score, like saying your model is 95% accurate, can be super misleading. I mean, what if that 5% of errors are all the most critical life-or-death mistakes? The reality is, in a lot of situations, the kind of mistake you make matters way more than how many mistakes you make. And we need a tool to measure that. And that tool is this right here, the confusion matrix. I know, it might look a little intimidating at first, but trust me, it's really just a simple scorecard. All it does is sort every single prediction into one of 4 boxes. True positives and true negatives, that's when the model got it right. Awesome. But the interesting parts are the false positives and false negatives. That's when it got it wrong. And by seeing exactly how it was wrong, we get some incredibly valuable insight.
And from this simple little grid, we can calculate way smarter metrics. Let's start with precision.
Precision answers a very specific, very important question. Of all the times the model raised its hand and shouted, "Hey, this is a positive," how often was it actually right? This basically tells you how much you can trust your model when it says something is positive.
Then you have its partner recall, and this asks a totally different but just as crucial question. Of all the actual positive cases that were really out there in the data, how many of them did your model actually find? Think about something like medical diagnosis. This is everything, right? You would much rather have a few false alarms, if false positive, than miss even one single person who actually has the disease. That's why recall is so critical.
Okay, so we can spot the problems, and now we have the right tools to measure them. So what's the game plan? How do we actually diagnose what's wrong with our model and, start fixing it?
Well, our number one diagnostic tool for this is something called the learning curve. It's actually a pretty simple chart. All it does is plot two lines over time: the model's error rate on the data it trained on, and its error rate on brand new data it's never seen before. And believe it or not, the relationship between just those two lines, it tells us basically everything we need to know.
And you know what? Reading these curves is surprisingly simple. If both of your error lines are way up high and they just stay flat, well, your model isn't learning anything. That's classic underfitting. On the other hand, if you see the training error dive down to almost zero, but the validation error stays high, creating this big wide gap between them, that's your model just memorizing things. That's overfitting. What we're always searching for, the holy grail, is that sweet spot where both lines slope down together and converge at a nice low point.
So, what's the prescription? Well, if your learning curve is screaming underfitting, the diagnosis is crystal clear. Your model is too simple. So the fix is to give it more to work with. You can either make the model itself more complex, add more layers, more neurons, or you can give it more clues by engineering better, more useful features from your data.
Now, on the flip side, if you're overfitting, the problem is that your model is too complex. It's getting lost, distracted by all the random noise. Now, the absolute, hands-down best cure for this is almost always just getting more training data. But if that's not an option, you can try simplifying the model, maybe use some techniques like regularization to kind of discipline it, or even just stop the training process early before it has a chance to memorize everything.
All of these concepts we've talked about, underfitting, overfitting, bias, variance, they're all pointing to one thing. They're all part of the single biggest, most fundamental challenge in all of supervised machine learning. This is the core of it all.
This quote here really just nails it. It says, to decrease the estimation error, you need to decrease both the bias and variance, which in general are inversely proportional and hence the trade-off. What does that mean in plain English? It means to make a model better, you have to lower both bias and variance. But here's the catch. They're like two ends of a seesaw. When you push one down, the other one almost always goes up. This is the great trade-off.
And this trade-off is what creates this classic U-shaped curve you see in machine learning. Over on the left, you have simple models that have way too much bias. Over on the right, you have super complex models with way too much variance. And our whole job, really, our entire goal, is to find that perfect sweet spot of complexity, right there at the very bottom of that U. And all of this leaves us with one final, really crucial question that every single data scientist has to answer for every project. You have to decide what kind of error you're willing to live with. So I'll leave you with this. What's better? To be precisely wrong or to be generally right? The answer you choose, well, it changes absolutely everything.